In this video, we'll be learning how to identify the domain and range of a variety of different function representations. So before we can actually identify domain and range, we have to start by talking about what domain and range actually represent. So the domain, by definition, is the set of all possible input values of a function. So typically where you're going to find these are all of the x values that are used to create a function and the representation that you see. So we're going to be looking at x values specifically when dealing with the domain. Now on the flip side of that, the range is the set of all possible output values of a function. And these are typically all of the y values that are used to create that function. So they're all of the y values that result as a result of those x input values. So we're going to see lists of x values and y values, and those will help us determine our domain and range. And then in other situations, we're going to have to visually look at the representation and decide what are all of the x values that I need and what are all of the y values that I need. So let's take a look at this example here. So here we see a coordinate plane with a number of points plotted onto it. And we remember that domain is going to be dealing with our input values or our x values that we need to create this particular graph. And the range is going to be dealing with the output values or the y values of this particular graph. So since I know I'm going to be dealing with x and y values, I'm going to start by finding the coordinates of each of these points because I know the coordinates represent the input x values and the output y values. So if I start with each coordinate, here the first coordinate is x is -3 and y is 0. I can see -3, 0. Then from here, this coordinate here, x is -2 and y is -2 as well. For this coordinate here, I have x is 0, y is 2. For this coordinate here, I have x is 1, y is -2. And then for this coordinate here, I have x is 5, y is 2. So I can see here that I have coordinates with x and y coordinate parts for each point. Now, from here, remember, our domain represents all of those input x values. So since I just have a list of coordinates here, I'm just going to list out all of the x values by writing x equals and then finding all of the x values that I can see on my graph. So here I have x equals -3, then I have -2, here I have 0, 1, and 5. And then my range, I'm looking at the y values. So all of the y values that I need to make my graph include, I see -2. I see -2 again, so I'm not going to include that twice. I'm just going to list it once. I see that I need a y value of 0. And then I see that I need a y value of 2. And again, because that one appears twice, I'm not going to list it twice. So here, all I needed to do, since I had a list of plotted points, was list out all of my x values and then list out all of my y values. Now, where this starts to get a little bit tricky is when we have to find the domain and range of a graph with a line and an arrow. So you're going to notice something a little bit different on this particular graph. What you're going to notice is you have an end point down here saying that the line stops. And then you have an arrow, and really what this arrow communicates on a graph is that this continues on forever in this direction. And so representing these, unfortunately, isn't just a list of numbers. We actually have to denote an entire range of values, and we're going to have to use inequalities. So if you see an arrow on a graph with a line that's going forever in one direction, you should be able to note that somewhere you're probably going to have to use an inequality to represent your domain and your range. Now, while this might seem a little bit tricky, it's really not too bad. You just have to think about it a little bit more deeply. So remember that your domain represents all of the input values or all of the x values that you need to make points on your graph. So when I look at this graph, what I notice is that this endpoint pairs up with the point x equals -3. And what I notice is that the graph really doesn't exist on the left-hand side of x is -3. Do you see that? How I can pretty much scribble out this part of the graph, and you can still see my entire line, because the entire line is still over here, and it's pointing to the right, so it continues to the right. So I don't need any of the x values on that left-hand side. The x values that I need to create this particular graph start at -3. You can see that, because that's where this endpoint is. They start at -3, and then the graph continues on to the right. So the graph continues to the right. So what happens is I need, all of these x values, all of these different numbers to create different points on the graph. I need this x value to create that point, and this one to create that point, and this one to create that point. And so what's happening is I need all of these x values that start at -3 and move to the right. Now, if you look carefully, this really represents a number line, right? So we have -3, -2, -1, 0, so on and so forth. I have a closed circle here, and then the graph, I'll do it right up above, is going to the right. And so because of that, the x values that I need start at -3 and then go to the right, which is where x is bigger than -3. So I can represent my domain by using my graph in the picture to say, well, the domain that I need, the x values that I need, they start at -3, and then they are all of the x values that are bigger than -3. And if I use all of those x values bigger than -3, I will be able to continue a graph to the right that will then ultimately create a graph that contains all of those points there. So that's how I can find my domain. I can visually see it by using the x number line on my graph. Now, what I'm going to do here is I'm going to erase all my scribbles, and I'm going to do this same thing for y. So again, I'm going to plot my point here. I'm going to show that my line fully extends on forever, noting that I'm going to need an inequality. And this time, I'm going to focus on the range. And remember, the range deals with the output values or the y values that I find on my particular graph. So if I look at my coordinate point, I can look over to the y-axis, and I can see that it pairs with -4. And so I know that the -4 is going to be an important part of my range. Then if I look here, what I notice about this -4 is that the graph, that line in blue, could pretty much exist even if the whole bottom part of this graph didn't exist, right? We don't need those y values on the graph. The y values that we need to create points on this graph are the y values that start at -4 and then work their way up. And so I need, this y value to make this point, and this y value to make this point, and, this y value to make this point, and so on and so forth. So I can see on this vertical number line that I have, and I know the vertical number line is a little bit weird, but it works the same, is I have -4, -3, -2, etc. And I need all of the y values that start at -4 and then go up and get bigger. So I can represent that in an inequality by saying, well, all of my y values, they start at -4, and then they have to be bigger than or equal to -4. So we can represent domain and range by using these inequalities as well when we have situations where we have an endpoint and an arrow that's implying that this graph continues on forever and ever and ever and ever in one direction. So let's take a look at this first example here. When I dive into this example, what I see is that I have two endpoints on this particular function. And if I see two endpoints, what that is telling me is that I'm going to have two inequalities in this domain and range representation because each ending point represents an inequality. So if I have two endpoints, I'm going to have two inequalities somewhere in my statements. We're just going to keep a lookout for that as we work on finding this domain and range. So let's start with the domain. And remember, for the domain, we're looking at all of the possible x values that are needed in order to graph this function that we see on the screen. Well, when I look here, what I notice is that this first endpoint right here pairs with x is -5. So I know that that's an important point on my number line. So I'm going to go ahead and plot that point there. Then, when I take a look at the other side, what I notice is that the 3 for the x coordinates is also important because it pairs with the other endpoint there. And then I notice that the line of the graph is caught in between these two x values. And if you look carefully, what you'll notice is you don't need any of the x values on this side of the graph. Notice that there's nothing graph-wise over there. We don't need any of those x values. And we don't need any of the x values on this side of the graph. We only need the x values sandwiched between -5 and 3 in order to create our line with our two endpoints on it. So if we think about this in terms of a number line, the x values that we really need are sandwiched in between -5 and 3. They start at -5 and then they go all the way up to 3. And this is a situation where we have two inequalities because we have a compound inequality here. Notice that x is sandwiched between -5 and 3. And if we look at this carefully and we write it carefully, we can say that x in one statement is on the bigger side of -5. So notice that, here's -4, -3, -2, -1, 0, 1, 2, 3. So x is going to be on the bigger side of -5 because we need it to fall somewhere in this range in order to be on this line here. And then x is going to be on the smaller side of 3. So notice that x is on the bigger side of -5 in this statement. You can see it's on the open side and on the smaller side of 3. And that's how we go about representing our domains and our ranges when they're sandwiched between two values. So you can see x is on the bigger side of -5 and the smaller side of 3. So now let's go ahead and repeat this process with the y values, okay? So now if we repeat this process with the y values, again, we're going to start with each endpoint. I notice this one pairs with -2, so I know that -2 is an important y value, and this one pairs with 4. And what I notice is that the graph uses all of these y values that are between -2 and 4. So I can leave it as a vertical number line if I want. I can also turn it horizontal if I want. But here I have -2, I have 4. I notice I'm starting at -2 and going up to 4. If you want to label some numbers in between, there's your 0, 1, 2, 3. And so I can see that x is sandwiched between these two numbers. And it is on the bigger side of the -2 and the smaller side of 4. So it's sandwiched between the two, bigger side of -2 and smaller side of 4. So again, notice that because we had two endpoints, and we noticed that x was sandwiched in between the two values, that we formed that compound inequality with an and, or a sandwich, of x between two different numbers. So let's take a look at this new example here. So this one doesn't contain any endpoints. This one contains only arrows. And remember, arrows communicate that this is going to go forever off of the screen. So you're probably looking at this without any endpoints. How on earth do we write a domain and range? Because there aren't any starting and stopping points. And that's true. We're going to take a look at what this graph is actually communicating to us. So if you look carefully at this graph, I know it's a diagonal, but if we focus just on these x values here, what we notice when this graph has arrows is that we need every single x value to make coordinates on this graph. We need x is 1 to make this point, x is 4 to make this point, x is 7 to make this point. And we're going to continue on forever because we need these points to continue drawing this graph on forever. And then the same thing happens in the negative direction. We have, x equals -3 makes this point, x equals -6 makes this point, and then so on and so forth, they continue. So essentially what we're noticing is that we need every single x value to the right and every single x value to the left to make points on this graph. And if we need every single x value to the right and every single x value to the left, that's telling us we need every single x value. And if we need every single x value, the way to denote that with domain and range is by simply writing all real numbers. So if you notice that a graph is going forever to the right and forever to the left in some way, even if it's at a diagonal, it's going forever to the right and forever to the left, and you notice that you need every single x value to make coordinates on that graph, you can simply write all real numbers. Now let's flip this around a little bit. Let's look at the y values. Again, because this graph is going up and down, I really need every single y value here. So I need this y value to make this point, this y value to make this point, and this y value to make this point, and so on and so forth. And the thing is, this graph is continuing on forever up and down as well. It's at a diagonal, but it is going forever up and down. And so as a result, what I'm finding is that I need every single y value as well, because this graph is going forever up and forever down, and eventually I will use every single y value. And if that is the case, we simply write all real numbers. So if you have arrows, you can actually start looking for instances where you may need all real numbers to make that graph. So let's take a look at this example here. The first thing I notice when I look at this graph is that I have 2 arrows. And because I have 2 arrows, I know that all real numbers might be a part of it because those arrows communicate that this graph goes on forever in both directions. Now, I know it might be tempting to write all real numbers for both domain and range for this problem. However, that's actually not the case. We have to be a little bit more careful. So here, let's take a look at everything very carefully. So if I take a look at the x values here, I notice that this graph is going horizontally left and right. So this graph is going forever to the right and forever to the left. If the graph is going forever to the right and forever to the left, it means I'm going to need every single x value to make points on that graph, because I need this x value to make this point, this x value to make this point, this x value to make this point, so on and so forth. So if I need every single x value, I can in fact write all real numbers. So now let's take a look at the y values here. Let's take a look at the y values. So let's erase our notes and let's take a look at y. Now what I notice here is that this graph is not going forever up and down. Really, truly, the only y value I need is the y value right here, because the graph doesn't tilt up or down. So I don't need any of the y values up here, and I don't need any of the y values down here. I just need this one single y value here of 4, because all of the entire graph is at y equals 4. So for that, if I notice that there's only one value that I need for the range, I only need one y value, I can simply write y equals that single y value, which in this case is 4. So the graph is going forever left and right, making my domain all real numbers, but because it's not going forever up and down and it only uses that one value, for the range we would just write y equals that single value of 4.